Welcome back. So, let us continue the discussion on the probability distribution function. So, we have looked at the distribution of CDF and how we get the probability distribution function, which is a derivative of CDF, and then we are now looking at the joint CDF, and we stopped at the property discussion. So, the properties of the joint CDF. Now, we look at the other properties of that. That means, if it is on V1 and V2, the joint PDF, so this would be the second derivative of this function f12. So, there will be one important property, the fundamental property is probability of u1, which is lies between V1 and VB, and u2 between V2 and 2B. That means, this is the space. So, this is how one can get. So, this is one of the important property of an joint PDF function or joint. Now, what is JPDF property? That it is one thing is that it is non negative. That means, f12 V1 V2, it should be greater than 0. It also satisfy the normalization condition. That means, minus infinity to plus infinity, which is 1 to V1 V2 dV2 dV1 1, and marginal PDF, where you get f2 equals to minus infinity to plus infinity V1 V2 dV1. So, these are the some of the properties of JPDF, joint probability distribution function. Now, we look at the joint statistics for, let us say, a function of Q, where you have u1, u2, then the central moment that is minus infinity to plus infinity, where q1, v1, v2, and this f1, 2 of v1, v2, dv2, dv1, something like that. So, one can look at the example of, let us say, I equals to 1 or 2, then n equals to 1, q would be u1 minus u1 bar and u2 minus u2 bar. So, this is an covariance of u1 and u2, and you can look at this plot, which is going to be minus infinity to plus infinity v1 u1, v2 minus u2, f12 dv2 dv1. So, essentially the, let us say, u1 and this is u2 and this is u2 bar and this is u1 bar. So, the mean correlation goes like that, where things could be scattered in this fashion. So, this actually two velocity component u1 and u2, that is a scattered plot, and this is how the covariance shows the correlation between these two variables. Now, if you look at the PDF of u2 condition at on u1 equals to v1. So, that means f21, where v2 is conditioned where u1 equals to v1. So, this would be f21 or 21 v2 v1, which is f12 v1 v2 by f1 v1. So, this you get from Bayes theorem. Now, the joint PDF of f12 scaled so that it satisfies the normalized condition, which is minus infinity to plus infinity f V2 condition V1 dV2 is 1. Now, the conditional mean of the function q u1 u2 condition at u1 equals to V1, where minus infinity q V1 V2 f21 where V2 V1 dV2. So, this is how you can see that these things. So, when you have the sample space and their condition on another thing. Now, one can look at the statistical description. Let us say U1 and U2 are statistically independent. So, that means what one can write F21 V2 V1 is F2 V2. Now, Bayes theorem gives us that F condition at V1 F1 2 V1 V2 by F1 V1, which is nothing but F1 V1 F21 V2 V1 is F1 2 V1 V2. Therefore, what we get F1 2 V1 V2 F1 V1 F2 V2. So, that means if you have independent variable, they are uncorrelated. So, in general the other one is not true, that means the uncorrelated things are not going to be always independent. So, this is what you get an idea about these different terminologies in statistical. Now, we using those statistical information, we look at the transport PDF based method, which is a statistical approach. So, this is like similar to your moment method. So, this is called the PDF transport equation. So, we get PDF transport equation for velocity and reactive scalars like mass fractions. So, this is based on 1 point statistics. Okay. Now, within that framework, we can derive a generic statistical description of these turbulent reacting flows. So, which will be independent of any combustion regime, and then we look at the joint PDF transport equation and the scalar, and that can be derived. This was proposed by Pope in 1990, and this has become quite useful in reacting system. Now, there are different ways to derive this transport equation for this joint probability density function. For P is variable V and psi, which is x and t, and but the discussion referring to the Pope in 2000 and 1985, so which write the convective terms in a conservative form like del T of rho P, the conservative equations of the probability density function plus delta dot rho Vp plus rho g minus del p bar dot del p summation of I equals to 1 to n del psi I WIP, which is del V dot minus del dot tau plus del P prime psi P minus summation of I equals to n del psi I, where del dot rho d del psi I, which is conditioned at V psi p. So, this is the equation or the transport equation for joint probability density function, which includes the velocity and the reactive scalar, where delta V, this is the gradient with respect to velocity components, and the terms which are within the angular brackets, these are conditional mean, and similar symbol have been used for the sample space variable. So, once we have this equation, we can see this is the equation that we have written. So, this is the del transient term, convection term, other terms. Now, the left hand side, the first two terms, so these two terms are the local change and the convection of the probability density function in physical space. So, that means this will lead to the material derivative essentially of rho p. These two terms will lead to that. Then the third term, which is this, let us say this is first term, second term, this is the third term on left hand side. So, this is the 1 plus 2. Now, the third term in the left hand side represents the transport in velocity space by gravity and mean pressure gradient, and this is the last term, which is the fourth term. So, the fourth term on the left hand side, it is an chemical source term. Now, if you look at all these terms on the left hand side, they are all in closed form. So, in the left hand side there is nothing because they are closed form, they are all local in physical space. So, left hand side you see there is no unclosed term. Now, while we move to the other side, now another thing one can note is that the mean pressure gradient does not present a closure problem, since the pressure is calculated independently of the PDF equation using mean velocity field. Also, so that means you can say mean pressure gradient. So, this does not present a closure problem, since the pressure is calculated independently of the PDF. So, for reacting system, the chemical source term needs to be treated exactly or properly. Now, always there have been an argument that respect to the transport PDF formulation, it has considerable advantage to other formulation, but obviously we can see what are those things. Now we will look at on the right hand side of that equation. So, there are two terms on the right hand side, term, this is first term and this is second term. So, these terms on the right hand side, they contain the gradient of quantities, condition on values of velocity and composition. So, the gradients are not included as sample space. So, if gradients are not included as sample space variable in PDF equation, these terms would arise as an unclosed term and needs modeling. So, there are issues, one has to be careful here. These terms are actually contain gradient, because they are all, and the gradient and also conditioned on velocity and scalar field. If the gradients are not the part of our sample space, then these need closure. So, one has to close this term properly. Now, the first term and the second term on right hand side. The first term, it is an unclosed term on the right hand side, it describes the transport of the PDF in velocity space induced by the viscous stresses and the fluctuating pressure gradient. So, the second term represents the transport in reactive scalar space or in the composition space by molecular fluxes. So, this essentially lead to the, or it represents molecular mixing. When the chemistry is fast, mixing and reaction take place in thin layers. So, chemistry fast, the mixing and reaction take place in thin layers where molecular transport and the chemical source term balance each other. So, the closed chemical source term and the unclosed molecular mixing term being leading order terms in the asymptotic description. So, the right hand side there are terms which are in asymptotic description, the flame structure and closely linked to the each other. Now, this has been already illustrated by Pope in 1984, the case of premixed combustion. When we compare a standard PDF closure for molecular mixing and with the molecular mixing term with formulation. So, the molecular diffusion term was combined with the chemical source term to define a modified reaction rate. So, there is the one distributed combustion and the flamelet combustion find considerable differences in Damköhler number dependencies. So, there are some issues which are there. Now, how do you get a solution for the PDF equation? Now, from a numerical point of view, the most apparent property of the PDF transform is high dimensionality. It is a highly dimensional. That is why typical your computational technique like finite volume or finite difference kind of techniques are not very attractive for this type of problem. Why? Because the memory requirements increases with the dimensionality. So, the virtually all numerical implementation of this kind of methods are using Monte Carlo kind of techniques which are particle based method, and the advantage is that memory requirement is not that much, and it's also can handle this high dimensional problem. So, this also you use some large number of particles, this is called notional particles. So, that means now so far our discussion, if you look at the Gaussian equation of the PDF transport equation, this is in a physical space in the Eulerian framework. Now, when you try to solve this particular equation, we are moving to a situation where we are introducing particles, that means it is a Lagrangian framework. Now, the particles should be considered different realizations of the turbulent reacting problem under this investigation. It should not be confused with real fluid element, and the statistical error and all these things also decreases with number of particles. Obviously, there will be an issue with the convergence, because once you have the high dimensional problem with large number of particles, these are obvious. Now, we can look at some of the basics from the statistics. One is the phase space, which we have already looked at, then distribution function, probability density function, mean, variance, joint PDF, covariance, conditional PDF and conditional mean. So, these are some of the properties which will be used, and we have already. Now, we look at this system, the physical space and the composition space. So, this is our physical space where the problem is defined, and this is one point which we want to locate. So, this is our sample space. So, the sample space possible variables are phi 1 to phi n s. So, that means if you look at it, the sample space is formed with all these scalars, they are sort of linearly independent functions one can think about. So, now for this particular point, one has to find out what could be the probability to have a certain composition. Now, one can find out the one point probability density function, which is the scalar PDF or composition PDF, which is defined at f phi psi x t. So, f phi psi x t d psi is probability of having phi j between psi j to psi j plus d psi I, where j goes to 1 to n s. So, in stationary combustion system, the PDF is time independent, and we can find out the mean. So, the mean would be phi k, x t would be psi k, f phi psi x t d psi, and variance, one can find out the variance, which would be psi k minus phi k square f phi psi d psi, and the covariance, which is C k l x t psi k minus phi k psi l minus phi l f phi psi x t d psi. Now, this is how from the distribution of the composition PDF you can find out this mean, variance and covariance. Now, if we look at the physical space problem is here, and we transform the velocity composition PDF. That means you have three velocity component variable and the scalar variable. So, they will form this total space, which is a joint velocity composition PDF, and one can see what is the probability to have certain compositions over there. Now, if you look at the 1 point probability density function, so the only velocity PDF you can write, this is the velocity. So, the probability of some sample lying between these two components, that is the probability of that. Now, the joint velocity scalar PDF, so it will be both on u and phi. So, this is velocity and scalars, and the probability of finding an event would be between a velocity component and the scalar component. So, now one can correlate the velocity PDF to, so the velocity, pure velocity PDF can be obtained from the joint velocity scalar PDF when you integrate over d psi, and the scalar PDF can be obtained when the joint PDF we took an integration over velocity variable. Now, we can look at this 1 point PDF for density weighted quantities, because this is very important. We have already seen that if we are dealing with reacting system, this density weighted average is quite handy to avoid all these density fluctuations that arise during averaging. So, now similarly for the joint velocity scalar PDF, this would be the density weighted quantities, and one can write rho psi by rho bar with this, and for scalar PDF or composition PDF, this would be written like this. So, now again coming back to our equations, this is our continuity equation, this is our momentum equation where we will get Reynolds stress, our scalar transport equation we will have source term and turbulent scalar flux. Now, these are set of Gaoni equations, and how we close that: Reynolds stress using some Rans based model, turbulent scalar flux, so you can use gradient assumption, and source term, the mean source term now we can close using composition PDF method. So, this is now the difference that we see when we are talking about other models compared to transport PDF based model. And similar things one can close it using velocity scalar joint PDF. So, this is Reynolds stress term, which could be using the joint PDF or velocity PDF, one can close it. So, instead of taking it from directly from the Rans equation, now we can use the Lagrangian information to close it. Turbulent scalar flux, which is this term, now we can close it using both velocity scalar joint PDF and source term using scalar PDF. So, that means all these closures are now done using the probability distribution function. So, this is an substantial difference when one look at the flow field in the Eulerian framework and when you look at in the Lagrangian framework in the context of transport PDF equation. So, we will stop the discussion here today and continue the discussion in the next lecture.